Okay, so we're going to start by building up what we can already know about for derivatives, and let's see if we can build this sort of pattern up. For the first example, I'm not going to do a proof with you because, for the sake of time and other things, we're going to leave that for later. If you do want to see it, it's in the textbook. But again, two important things. Let's put them out there and let's make sure it shows up on YouTube. So what is a derivative when you're finding it? What are those two things I want you to remember every time you hear the word derivative? Tangent line. So tangent line is great. That's one of the ones I'd like you to think of. What's the other one? The slope, which represents rate of change. Okay, so that's what we're going to work on today here. So if we have a constant, like y equals to 2, then what do you think the derivative is going to be for a constant?
0.
Well, why is that? 0 is correct. Why? Horizontal line. And explain it to me the other way that you should be thinking of a derivative. Slope is 0, which means the rate of change is 0. It's a constant. There is no change. So since there's no change in the graph or the function, the derivative will be 0. Okay? So you can safely assume that whenever you run into a constant, it would have a derivative 0. Find the derivative. Now let's just see here. For the line y equals 5x, what would the slope be for this? 5. Yeah, that's right. Why? Because that's the slope. Yeah, you can see it right there. Every point that would be tangent would have a slope of 5. So yeah, we can just put that one down as 5. That's okay for us now. How about 3x squared? What I'm going to do is... Oh, people are thinking ahead. Okay. What I was hoping was some of you might know a shortcut on this, but this is the way you can think of it, as two separate pieces, and hopefully you remember what happened to x squared from your homework in our other lessons. Do you remember what happens to just x squared when it has its derivative?
2x.
Yeah, it became 2x. So this would be like 3 times 2x, which would be 6x. So yes, it would be 6x. And we did an x cubed as well. Do you guys remember what happens to x cubed?
3x squared.
Yeah, 3x squared. So hands up, we're using a shortcut someone taught you to do? Okay, fine. Fair enough. I just thought you were geniuses. You should have left your hands down. Okay. So this is the power rule for a derivative. It's written in this notation, the derivative with respect to x. So that's what the top part means, the derivative. The bottom part says with respect to x. So if I have some power like x to the n, then the derivative is going to be n times x to the n minus 1. So let's take a look at the ones we've done previously and see how that relates. Okay, so for example, in the first one, 5x, that's like 5x to the 1. 1 gets pushed to the front, so 1 times 5 is still 5. Then x to the 0, it's gone, right? That's just going to be a 1. This one here, it would be 2 times 3 becomes a 6, and then the 2 becomes a 1. Same thing here, 3 to the front, decrement at 1 time, becomes 3x squared. So the power rule is a nice simple one. Again, there is a proof provided in your textbook if you want to see why that is. But anyway, for us, our purpose is good enough to know this definition, and we will use it all the time, all the way up until our exam. So I doubt you're going to forget this one, but it's not provided, of course, on any formula sheet. So let's find some derivatives. What do you think 7x to the 6 would be? Yeah, so it would be, that number comes to the front, so it would be 7 times 6, x to the 5, which is going to be 42x to the 5th. Now, the next one looks really complicated, but it's really just because we've written it it's not the most convenient way to look at it. Could anyone think of a convenient way to rewrite x cubed square root? Yeah, that's another way you could think of this. Okay, now it makes more sense to use the power rule because you can see the exponent. So this would be 3 halves x to the 1/2 when I take it away. or square root x, whatever you like. Okay, how about the next one? The next one's not very convenient either. Okay. There is sometimes this tendency, and this is not where we're headed, for people to go like this. That is totally dead wrong. Can anybody explain to me what I did wrong or why I did this wrong? Yeah, this is on the bottom as x to the 4. Really what I should be doing is I should be writing it like this. That's 1/2. And what I'm actually looking at is x to the negative 4. So the power rule I've given you so far, it only works for like an x to the something. Not a 1 over x. You know, nothing else that's been combined with it. Only when you have x to an exponent. Okay? So it wouldn't work in this situation because x is on the bottom. There's a whole bunch of other stuff happening here. Okay? So if we do the power rule now, it's going to be 1/2 times negative 4. And what's the exponent?
Negative 5.
Yeah, negative 5. Be careful. Sometimes people want to say negative 3. But it's actually one lower. You take one away, it would be negative 5. Okay, so this would be negative 2 x to the negative 5. Or if you want, you could, of course, write it as negative 2 over x to the 5. Way better than limits, huh? So much better. Like, that would have taken you an hour to do those 3 derivatives. Anyways, okay, but shortcuts are good thing, but you can't forget your limits that we did the other day. So all I'd like you to do for this next couple is, between you and your neighbor, I'd like you to try rewriting these in a convenient way to use the power rule. Okay, so if you can rewrite it, chances are you can find the derivative. That's your job. Go for it. Okay, so I've had a chance to see some of you guys at work, and it looks like you're getting the hang of it. So I'm going to catch up to you. You can double check over on the board here. I would have rewritten this as 5/2 x to the negative 3, which means the derivative would become negative 15/2 x to the negative 4. For the next one, I would have rewritten this as 7/3 x squared. So it's going to be 14/3 x. And for the last one, the whole thing is in brackets. So I would have chosen 3x squared. And I haven't told you how to work with what if there's more than an x there that's being squared. So hopefully you figured out just to do this. And this would be the most convenient way to start with it before you use the power rule. Okay, everything's expanded out there. It's going to be 126x for the derivative. Okay. So hands up if you got 2 out of 3. At least 2 out of 3. Good. Okay. So just to confirm a few rules for you. If we take the derivative of with a constant involved, we've already been playing around with this, but the derivative, if you take a constant times the power for the power rule, it's the same thing as if you pulled the constant out and take the derivative separately. So sometimes you may need to exploit that rule like we did in these last 3 examples. Okay, so perhaps that should be before it in your notes, but anyways, that's legit. The other legit thing is, if we want to add or subtract, we could take 2 separate powers. For example, I could try and take the derivative of x to the n and x to a different number m. It'd be the same thing as doing them separately. So the reason that this is good news for us is now we can do a whole polynomial. We don't have to worry about what happens in combination. The combination, for example, like x cubed minus 4x plus 5, we can just focus on each piece. Now, we're going to spend some more time later when we look at differentiation techniques. It's not so simple when it comes to multiplying and dividing. So in your homework tonight, you shouldn't be doing anything that involves multiplying derivatives or dividing derivatives. It means you missed something along the way, or simplifying didn't happen properly. Okay, today the only things you should deal with are constants and adding and subtracting. Otherwise, you need to think about how you could rewrite it. So, let's see who's on the ball. Let's see, can we do these 2 in 1 minute? Let's see, 1 minute. On your mark, get set, go. So let's see how you did. This here should be 3x squared minus 4. the derivative here, multiply the 4 in front, it'll become -2, and then x cubed plus 9x squared minus 2. Okay? So, is calculus looking a little bit friendlier? It's not as scary? Okay, so this is, so far we've been talking about polynomials and how to deal with them. Now we're going to talk about how to deal with trig functions. So the two most common ones you're going to run into, we'll talk about the other ones in separate classes, but these ones, you're going to use these a lot. So the derivative for the sine function might surprise you. It's actually the cosine function. The derivative for the cosine function, what do you think?
Negative sign.
Oh, you guys are cheaters. Yeah, it is negative sign. There's a negative in there. So all I'm going to do is I'm going to sketch this proof out for you. I'll show you how the proof goes. You can handle this. It's not a bad proof. So for now, you may want to copy it in your notes. You may just want to follow along and see if you understand how the proof works. Okay, so I'm going to do it on a separate, larger note. Okay, so what I'm trying to do is, I'm trying to prove that the derivative of the sine of x equals cos x. So the only way we can do this is to use the definition and magically end up with cosine. So you guys are capable of all this, and I think you should be able to follow it. If I use the definition, I'll be at x plus some delta x, take away the sine of x, and I'll be dividing it all by delta x. Okay, so far you're okay? This is the definition of the sine derivative. What will we do here in Math 12? Any ideas? Sure can't do anything with it as it is. Does anybody recognize this? Huh? It's an identity, yeah. So I'm going to use the identity. And what I'm going to do is I'm going to write this out using sine x cosine delta x plus cosine x sine delta x minus sine x.
No,
So
that's actually not that bad. I remember.
It's this piece here is this identity here. And don't worry, we have time to review Math 12 and we need to do it later this year. You wouldn't be expected to do this. I'm showing you why this is as it is, okay? So now what I'm going to do is I'm going to do a little bit of algebra to help me out, and I'm going to combine, just so I can see it better, it's going to be those two pieces. Okay? So it's going to become the limit as delta x goes to 0 of sine x. So it's these two pieces that I'm looking at, and I wanted to factor it. The other piece I haven't touched is here, so I'll add it back in. And now, the reason I did that is I actually see a couple of those fancy trig limits we talked about last unit. So it's going to help you if I rewrite this. I'm going to, instead of having the 1 fraction, I'm going to make it like this. Okay? Do you guys recognize any special trig limits in there?
Sine delta x over delta x is 1.
Okay, so there we go. That one is, oops, sorry, not 1. It's gone to 1. Okay, and what about another special one? Anybody notice another special one in there? Yeah, what does this turn into?
0.
Okay, so what's the only thing that survived the limit?
Cos x.
So there you go. Using the definition, it winds up being just cos x.